Hello, good morning. I think this is week 11 lecture, and for today we're going to look at an example. Then we're going to compare with Tresca and von Mises criteria. Then we're going to go into fracture criteria for brittle material under plane stress. So now you guys know what plane stress actually means. Means stress in one direction is equal to 0. So the example I'm going to do is the same as what we have done yesterday. Okay, so this is example number 1. So yesterday we did this same question, but we use maximum distortion energy. Today we are going to apply maximum shearing stress criteria. Okay, so we have the condition. So as we know, we are aware that the diameter is 1.5 inch. So we have written out our radius equals 0.75 inches. And the yield is given to us is 42 times 10 to the power 3 psi. Right? And the load P is equal to 60 times 10 to the power 3 pound force. Okay, so this is force. So we're going to base on the Tresca. Right? So maximum shearing stress is based on Tresca criteria. So based on Tresca criteria, we know that the stress, the maximum shear stress, okay, max is equal to stress yield divided by 2. Alright, we know that this is equal to stress yield divided by 2. So we know that tau max over here is 42 times 10 to the power 3 divided by 2. So we know that is the yield over here is 21 times 10 to the power 3 psi. Okay, so that is, so we have formed the limits of the mole circle. Okay, we later on we have to check. So again, what we're going to do is we're going to draw our transformation. So we're going to follow our transformation yesterday. Okay, so we're going to follow. So if I'm not wrong, I'm going to refer to our Tuesday lecture. So X, Y, and Z, got it? So X, Y, and Z. And we're going to have our element over here. Okay, this is our element. So we pick up this element. So similar like what we've done yesterday. So we have X, Y, and Z. Then we look at our element. Okay, so this is our Z direction. So we know that we're going to have a compression. So stress Y. We know that stress X is equal to 0 based on the rotation of the torque. The element will distort in this manner, right? Because if we hold one end, it will distort the other end. So we know that we're going to have positive shear. And we also know that stress Z is equal to 0, and we are aware that this is the one that, so the shear is equal to TR over J, and we know that this control the torque. Yeah, this control the torque. So from here we have to find, okay, what is our shear XY. Okay, so we're going to plot mole circle, but before we plot the mole circle, and it's going to be based on Tresca, and this is also equal to the radius of the circle. Okay, this is also equal to the radius of the circle. So from here, we're going to look at our mole circle now. Okay, so we're going to sketch our mole circle, just roughly sketch. Okay, so roughly sketch. So the same thing like we have done before. So in fact, I'm going to copy the exact mole circle. Is going to do exactly the same. No, it's too untidy over here. I'm going to draw it quickly. Okay, so some of you might forget. I'm going to do it quickly. It's very quick. So if you want to quicken it now, okay, by all means do so. Okay, or ×2 on YouTube. So this is our mole circle. Right, so this is our shear, clockwise and the clockwise. So by looking at our element, right, we're going to call this point X, point Y, and point Z. Now what we are trying to do down here is we are trying to make sure, okay, why draw mole circle? Why construct mole circle? Okay. So why we do this, we want to ensure that the maximum shearing stress is in plane. Okay. If it's out of plane, we have to know also. Okay, we have to know also. Right. So we know that this is our stress X line. Our stress Z line is also over here. And then we know that it's going through compression. Right, let's go. So this is going through compression. Right, so this is our stress Y. And then we know that there's a possibility that one is here. And the other one is down here. Okay. Okay. So by looking from at here, we know that at point X, right? Point X is 0, anti-clockwise. Point Y over here is a point Z. Okay, so you can draw a straight line across. So this is your stress average. Okay, so that's your stress average. And then from here, right, from here, you can draw a mole circle now. Okay, so mole circle, I'm going to vaguely try my very best to sketch this out. Hey, mole circle, not mole square. Sorry. So I'm going to try. Okay, so sorry. So I believe this is our circle. Okay, so this is my estimate. Okay, so this is our mole circle. Right, so this is our first circle that we have drawn. Okay, so we know that this circle over here, it belongs to our XY plane. And then we construct another one. And we have confident now, right? So 1. This belongs to our exact plane. And our last circle, 2, 4, 6, 7 and a bit. Our last circle is over here. So the last circle over here belongs to your YZ plane. Okay, that belongs to your YZ plane. So as we can see over here, if you look at the biggest circle now, right, we check. It happened to be your tau max, right? So this happened to be your tau max, and your tau max is also equal to your shear in XY plane maximum, right? So it's on your XY plane maximum. So you check, and you know that this is equal to 21 times 10 to the power 3 Pascal. Okay, so you check. Now there's a possibility where there are situations when this is not the case. Okay, is where stress Z also has compression stress. So I'll give you an example that this is not possible, or your maximum shear stress. So condition where maximum shear stress is not in the X or in the XY plane or in plane. Okay, so we have another possibility that when it's not, is when this happen. Okay, when this happen. So again, you have your stress, normal stress, and then you have your shearing stress. Okay, you have your normal stress, you have your shearing stress over here. So this is your normal stress, and then you have your shear stress clockwise, anti-clockwise. So your stress Z is still on this line, but then you're going to have possibility. I know some of you might ask. I know exactly if I can visualize the student's face now. So this is your stress Z, or stress Y, stress X, and then you have over here. Okay, so these are your shear. Let me draw a bit bigger. Hope this work. Yeah, I think will. Right. And then you have your stress X here, and you have your stress Y here. Right, so we have condition where you have a loading situation where this is the case. So you draw a line across, right? So two screw. So you draw your mole circle. So this is your mole circle. Right, so this is your mole circle. Okay, good enough for my circle, I hope. Okay, so maybe it's not that perfect, but it's good for me. So you realize that this is one your circle, right? And then this is your what? Now this is your XY plane, right? And we are told that the maximum shearing stress is I'm having to is the radius, yes or no, right? But are we sure that it's a maximum shearing stress? So now if we have a Z point here, right? So we have another circle now, right? We can draw another circle on our Z point because Z point has no stress. So this is 1 and a bit. So this is our the other circle, and this circle correspond to our XZ plane. And then our final circle, right? So 2, 4, 6, close to 7, 3.5. Right, so our final circle is somewhere around here. Okay, so this is our final circle. Oh, sorry, moving the wrong circle. Right, so that is our final circle over here now. Okay, so this is our, as you can see, this is our YZ plane. So now the maximum shear, you can see down here now, I'm going to draw, right? It's no more your what? It's no more on your XY plane. So now your tau max, so the statement is not the same. Now your tau max is equal to your shear in your YZ plane, okay, or max, right? And this will correspond to your 21 times 10 to the power 3. So from here, you cannot use your 21 times 10 to the power 3, okay, to calculate your torque, right? So this is where it's critical to check whether your shear stress is in plane or out of plane, okay? I'll come back again. Thank you for part 2 of the video. Sorry, I'll come back again for part 2 of the video. Thank you.